In section 6.3, we're going to talk about exponential functions again, but we're also going to talk about something new called logarithmic functions. So up to this point, we talked about exponential functions, which look like the following. So exponential functions that we learned about in this chapter look like a base that is some number, and then the exponent is the variable. So something like this, 2 to the x. We can also look at different bases, like a base of, let's say, 1/2 to the x. We can also look at other bases like 3 to the x, e to the x, 10 to the x. These are all bases that we see a lot. So it could be a fractional base that's less than 1, like we were doing with graphing, or something that's bigger than 1. It could be e, it could be 10, it could be anything. But we're also going to discuss something called logarithms now. So let's take a look at what logarithms look like. So logarithms. Logarithms, we'll see a log is a shorthand for logarithm. They'll have a base as well, but it'll be a subscript, means a little small number next to the log. And then we'll have whatever is going to get plugged into your log next to it. That will be a big number. It will be not part of the subscript. So this is read as log base 2 of x. Just another one that would match up with the 1/2 as a base would be a log base of 1/2. Again, we can still plug in x's. Another example would be, let's say, log base 3 of x. Now, log base e of x, that got used a lot. So I think that people got tired of writing that. So they shortened the hand on that and stopped using log base e and started using what's called natural log of x, which I know it says natural log is what it's called, but it's written out as L first for the log, and then the N actually comes second for natural log. So if you see natural log ever, even though you don't see a base, a little subscript, it's always understood that if you see a natural log, it's automatically a base of E. There's one other special log, and that's a log base 10. And again, it gets used a lot, so I think people kind of got tired of writing this out. So they started writing out just a regular log with an x. So what this means is if you ever see an logx with no base, it's understood that if you don't see a base on an log, it's automatically a 10. Kind of like whenever you see a root and you don't see a number, it's automatically a square root. If you see an log without a base, it's a base 10. If you see an ln without a base, it's always a base e. Now the question becomes, why am I talking about logarithms and exponentials at the same time? Well, here's the punchline. They are inverses of one another as long as their bases match up. So what is going to undo or be the opposite of a 2 to the x is a log base 2. And in reverse, what's going to be the inverse or opposite of a log base 2 is going to be an exponential base 2. What's going to be the inverse or opposite of a exponential base 1/2 is a log base 1/2. What's going to be the opposite or inverse of a log base 1/2 is an exponential base 1/2. Keep on going. The same ideas are going to apply. What's going to be the inverse or opposite of an e to the x is we don't use log base e, we use natural log. What's going to be the inverse or opposite of a natural log will be the e to the x. What's going to be the inverse or opposite of the exponential base 10 would be, we don't use log base 10. We use just a regular log. So that will be its inverse. And what's the inverse of the log, which is, again, automatically a base 10, will be a exponential base 10. So these are all inverses as long as the bases match up. And remember, inverses undo one another. Another way of remembering inverses is, remember, you swap your x's and your y's. So that's a quick reminder about inverses. How do you find inverses? Remember, for inverses, you swap x's. You swap x's and y's. That's how you find your inverses. But notice with these, when you're finding your inverses, whether it's an inverse of a log is an exponential or the inverse of the exponential is a log, notice that the base stays the same. That's very important. So let's play around with this idea of how the exponentials and the logarithms relate because they are inverses. Okay, what does it mean for two things to be inverses? Well, if I have 2 to the third equals 8, I can rewrite that as an equivalent logarithmic term. Why? Because they're inverses. The base would just stay the same. So what's the base of our exponential here? Well, it's a base of 2. So I could rewrite it as a log base 2. Except for what I need to think of as my other two numbers, my 3 and my 8, treat those as like an x and a y. Well, if we're talking about a log being an inverse, that means I would need 2. Remember, with inverses, we swap our x and our y. So, well, on the exponential, the 3 is with the 2. If we swap our x and our y, that means the 8. When I'm looking at the log with the same base, will be with the 2 instead of the 3. That means the 3 will actually move to being on its own on the other side. So our equivalent statement as a log using inverses would be that the log base 2 is of the 8 this time. The 3 is now on the other side by itself because we swapped the x's and the y's, but we kept the base the same because they are inverses. So let's try this out. Let's look at A. On A, we have 2 to the 5th equals 32, which we know is a true statement. We want to write the same statement, but we want to do it in logarithmic form. And what that means I need to do is I need to use my properties of inverses. So if we have, like we do in this one, an exponential that's base is 2, it's going to turn into, when we use our inverses, a logarithm base 2. But, because I'm using rules for inverses, I need to swap my x and my y, which are my 5 and my 32. So if I swap the sides on my 5 and my 32, my x and y, it'll be log base 2 of 32 equals 5. That's it. Let's look at B. On B, I have an exponential base 2/3. So when I use, again, my properties of my inverses, I'm going to turn this into a log base. It'll look a little funny. Log base 2/3. That's, remember, a subscript. But then again, just like the last one, I have to, because they're inverses, swap the x and the y, the other two numbers. The -3 and the 27 over 8. So the 27 over 8 is going to be on the left-hand side now, equals the -3 will be on the right. And that's it. So we'll have log base 2/3 equal of 27 over 8 equals -3. Last one, let's look at C. So let's see, what do we have here? On C, we have an exponential base E. So what's the log that matches up with that? Would be the log base E. Well, we don't use log base E. We actually use special one. We use ln, the natural log. Just like before, though, we have to take the x and the y. the other two numbers and swap because they're inverses. So that means that natural log of 1 will equal 0, swapping the x and the y, and we're done. Now let's do the reverse. We're going to take a logarithm and write it as an exponential. We're still going to do the same thing. We're going to use our rules for inverses though. So if we have, like we do on this first one, a log base 5, we have a log base 5, we're going to rewrite it as an exponential base 5. But just like before, we're still dealing with inverses. We have to swap the x and the y, the other two numbers. Well, remember this is an exponential function though, so when we move the 1 over to the left-hand side, it's going to be the exponent on that base of 5, and then the 5 will be on the right-hand side by itself now. What's cool about this direction with exponents is you can make sure that your answers are actually making sense. Well, does 5 to the first power equal 5? Yes, it does. So this is exactly right. This is a statement that it turns into, and it is a true statement. So this is what we've got. The statement 5 to the first power equals 5. Now, let's look at the next one. On B, we have a log base. Let's see, we have a log base 4. So when we use our properties of inverses to rewrite this in exponential 4, it'll still be a base 4. The only difference is we're going to be swapping out our x and our y, the other two numbers. We'll be swapping those out. So when the negative 3 moves over to the left-hand side, we're now dealing with an exponent, so it'll become our exponent on our base here of 4. So it'll become a negative 3 here. Equals, now the 1 over 64 will be on the right-hand side by itself. Now let's make sure that this makes sense. We've got 4 to the negative third equals 164. What does a negative exponent do? Remember, it drops itself to the bottom of an fraction, so this would become 1 over 4 to the third. Well, we know that 4 to the third is 64, so yes, this is a true statement, and that's what we were looking for. The exponential form is saying 4 to the negative third equals 1 over 64, and we do know that that is definitely true. Let's look at C. In C, we have log base 3. So this would turn into, when rewritten, an exponential base 3. The only difference is we again have to use our rules of inverses and swap our x and our y, which means the exponent on my 3 is actually going to be, the 2/3 is going to move over there. Will equal, the cube root of 9 will move to the other side. And there's our equivalent statement. Now, to make sure that this makes sense, which it does, remember the 3 on the bottom tells you what kind of root you have, which is a cube root. You'll have a cube root of what? Well, 3 squared, which is 9. So, does this make sense? Absolutely. So, our final answer is that 3 raised to the 2/3 equals the cube root of 9. That's the exponential form of this equation. One last problem. On this last one, we have a log, an LOG. We don't see a base, though. Remember, if we don't see a base on an LOG log, it's a hidden base of 10. You still have to do what we've done before, which is take your other two numbers, which kind of treat those as your x and y, and swap those because they're inverses. Now we're dealing with the inverse. So our exponent on the 10 should be 2, and that should equal 100. Well, 10 squared is 10 times 10, which is 100. So yes, this is definitely a true statement, and that's my exponential form I was looking for, that 10 squared equals 100. Now we can go ahead and use this trick to actually solve equations. So if we look at problem A,